meeting. Okay, great. Meeting. Okay, great. So I'd like to start using this slide just to review about the regression strategies that we delved into in the last class. I gave you some clues how to do these regression steps, and I recommend you to use a few regression variables in the beginning, because just to figure out what is going on during the regression part, the regression steps that we try to follow in your exercise. After that, we can add more variables in your project, just and see the impact of these variables in the results. So I gave you these recommendations on some key properties that you need to include in your project in order to get the matching between the prediction of the equation of state and the lab experiment that you measure in advance. So some key properties are the binary interaction parameters. I think we should include in your project. The correlation parameters that controls the prediction of the viscosity behavior, and the properties of the heaviest component, a heaviest pseudo component in your mixture, because this component is the component that brings the highest uncertainty in your composition analysis. You have a lumping of components inside a single component, so only a single set of properties is used to characterize all those components, including this lump component. Okay, so this is the most important property for us, parameter for us in the property. Maybe today I will explore the variables boundaries. So we need to take care about the range of the variables, and sometimes we can change the range in order to get good results in terms of matching. Another key clue: don't include pure components in your project. Please don't use methane or C2, C3 component, because in this case we know about the properties of these components. There is no uncertainty, or the uncertainty is much lower than when you compare, for example, with the heaviest pseudo component. So I don't recommend you to use those pure components in your strategy. Another important point for us: don't mix viscosity and PVT data at the same step. Please do the regression of the equation of state beforehand, doing the regression of the viscosity correlation. 2 steps. And the third step will be the solubility model. So we can do 3 steps in separate ways. So you don't need to match everything simultaneously. And don't forget, you need to try. You need to do several steps, and because this exercise is a try and error exercise. It's part of the game to test, to modify, to change the project, to do again. So be careful, be patient, and persist, because you need to test and see how you can improve the matching, especially using weights. Use weights to give more weight for a specific property in your objective function. Remember, all these exercises is an optimization problem. You are solving an optimization problem. So it's part of the optimization to build the objective function. And in this objective function, you need to include the parameters and the weights. So it's 2 things that you need to include, and you can do this using WinProp, for example, to conclude this exercise. Okay, we discussed the idea, just to sum up the main task that we discussed last class. We start doing a project for oil. Okay, following these 2 steps. First, the equation of state matching, and second, the viscosity model matching. keeping frozen the previous matching of the equation of state. Okay. This table is to guide you. Please save this table and refer to this table every time that you need to see and to check what's the level of accuracy that you can pursue to assume that you calibrated your equation of state according to a specific property. For example, if I can consider my equation of state calibrated in terms of BO prediction or in terms of GOR prediction, you can use this as a criteria to compare if your prediction is in agreement with the lab data. So this is the accuracy that you can pursue doing your regression strategy. Okay. We solved this exercise last class, and the idea today is to move to gas property, because our main goal in this training course is to discuss about gas mixture, hydrocarbon gas mixture, or gas mixture between hydrogen and CO2 and other gas, but the strategy is the same. Regardless the composition of the gas, we can follow the same step to calibrate our model. So I just need to discuss a little bit about pseudoization. Okay, pseudoization is the reduction of the number of EOS components. Sometimes, especially when we are dealing with gas depleted reservoir, sometimes you need to reduce the number of components in order to make faster your simulation, your compositional simulation model. So this is a connection between the fluid modeling and the numerical modeling. You can use, for example, your compositional analysis can have 9 components, for example. However, if you export your equation of state with 9 components, the simulation model will be very slow. So you need to reduce the number of components in order to reduce the number of equations to be solved in your system by your numerical simulation. So this is part of the game to do this pseudoization or lumping process. Another name for this, I think the most popular name is to call this as lumping. Is another name. And the basic idea is to, instead of working with 9 components like this, is to reduce the number of components, create more pseudo component. So this is the pure component, and now I will work with pseudo component or fake component to represent the fluid. For example, in this case, methane is a pure component. Most of the time, I don't lump methane with another component. I can lump, for example, with nitrogen. Nitrogen is very convenient because it's a light component like methane, based on the similarity in terms of molecular weight between methane and nitrogen. A good approach is to lump both components in a single component. So sometimes I can, if you have nitrogen in your composition analysis, you can include the nitrogen together with methane in the same pseudo component. Another strategy is to lump components like ethane, C3, and C4 in the same pseudo component, and I can generalize and can lump other components and generate new pseudo components. So the general idea is to reduce the number of final component the intention is for your numerical simulation. Okay, it's not to represent the fluid itself. It's the fluid representation, but with the eye on the numerical simulation. Keep an eye on the numerical simulation. How will be the performance of numerical simulation using this fluid model that you are previously doing in your simulation, PVT simulation package. Okay, so we need to answer this question. Okay, how I can lump the component how after that I need to do some regression using the new composition, okay, and to define the final number of components to be used in the numerical simulation. So there is no clear rule about how to do this, but we can do try and error, and I can share some rule of thumbs with you, some guides, some clues how to do this. For example, we can lump iso and normal fraction. For example, IC4 and NC4. You can lump both in a single component called C4. The same for IC5 and NC5. Another thing, you can lump nitrogen and CO2 and C1, for example, because both are light component. Another recommendation is to lump CO2 and methane, okay, in the same component. However, be careful, because if you are planning to inject CO2, please don't lump CO2 with another component. Keep CO2 as a separate component. The same for hydrogen. Okay? If your project is a CCS project, CO2 is the key parameter for your project. So CO2 in this case has to be a separated component. Okay? Don't lump CO2 with other component. This clue is only for the case that you have a small amount of CO2 in your in situ fluid, and you are not planning to inject more CO2. So there is you don't expect variation or huge variation of in the amount of CO2 over the course of your simulation, your numerical simulation. So it's important at that point to think about the use of this fluid model in your numerical simulation. It's not only the focus is not only on the PVT simulation itself. You need to keep an eye on the numerical simulation, the use of this numerical fluid for the next step. So if you are injecting CO2 for CCS, CO2 has to be a separate component. The same for underground hydrogen storage. In this case, hydrogen has to be a separate component. If you have cushion gas in the hydrogen component, the component that is used as a cushion gas has to be a separate component as well. For example, if you use CO2 as a cushion gas, CO2 has to be a separate component. If you use nitrogen, or if you use methane as a cushion gas, they have to be a separate component. Don't lump because you will inject this component and you need to have control about the properties of this component and the effect of this component in your mixture, okay? Take care of this. Keep in mind how you want to reduce the number of components, however, you cannot generate an artifact, a numerical artifact. You need to be very careful and strict with the number of components and the representation of this modeling in for your numerical simulation. Okay, so try lump light component first. Yeah, we start with the light and go to the heavy. It's a good strategy. And be careful. You need to lump, but you cannot deteriorate your prediction. So it's a try and error. Try one strategy for lumping and see the impact. To test if you are able to match the lab data using that strategy for lumping. If you are not able to match the lab data with that strategy, change your strategy. Try another strategy and compare the prediction between the equation of state and the lab experiment. It's a trial and error, okay? Let me show, I want to show first this table. This table shows some ideas, some schemes for pseudoization, okay? This is the original, this column represents the original composition analysis you have from nitrogen to some fake components. Here it's not clear which components are that, just to represent just examples, not a real case. And step one, it's very common to lump nitrogen and C1 by similarity, okay? Another strategy is to lump CO2 and C2 if the amount of CO2 is small, less than 2% in mole, okay, molar fraction, and if you are not planning to inject CO2, okay? It's important to keep in mind this concern. Another strategy, you can lump the iso and the normal component. IC4 and C4 is represented by C4, IC5 and C5 can be represented by C5, okay? And now we can try to lump the light component. You can try to group C3 and C4 in a same component, and C5 and C6 in a same component. Take a look, the original 13 parameters or 13 components, now you have 6 components. So you reduce from 13 to 6 pseudo components. You can do more, but for me, this is enough. I think, in my opinion, I think we can stop this strategy. But if you can try something more more aggressive, you can try to combine any two C1 and C2. I don't like this combination, okay? Because C2, you cannot generate condensation of C2. So there's I don't like this. I don't recommend to do this. But you can try to do sometimes, or you can try to work with 4 pseudo components. I think 6 for this case, for this gas, should be good enough to for your numerical simulation. Okay. So yeah, sure.
What are these F1 and F2, F3? I think they are pseudo components, but how do you like do the pseudodization based on stages for F1 and F1, F2, and F3?
In this case, as a gas mixture, the amount of F1, F2, 3 should be very small. Okay, should be very small. But in some case, for example, you can try to lump the heavier components if the amount of these heavier components is very small. So maybe you can reduce the number of the heavier components in the mixture. But it's not clear. It's not clear in this case what is F1, F2, and F3. It's not clear, but we can do.
Gas condensate is C7 plus only. Like it seems like it is more than C7 plus here. Like maybe F1 is C7 plus, or F2 is C20 plus, or maybe C3 is C30 plus or something.
Probably, yeah. I think so. Yeah, probably. Represents components with more than 7 components. So I assume that those components for this mixture, those components are too small in this mixture. Okay, maybe we can try to reduce. But the idea is to give you an idea how to treat the pure component or the light component. Okay, so the idea here is just to give you an example how we can play with the light components in the mixture, but heavier the heavy components should be used to lump as well. Okay, I will give you some examples. So another idea is just to compare. Basically, there is no science behind these, more practical clues that I want to share with you. For example, for depletion process, for lean gas production, dry gas production, maybe 3 or 4 pseudo components are sufficient. It's almost a black oil simulation. Black oil simulation is you can represent your mixture by 2 components, one for oil, another for gas. So if you are working with a 3 and 4, you are very close with the number of phase or components of a black oil simulation. Okay. So for depletion process, such as in dry gas production, this strategy can work very well. Okay. For compositional system, more compressible system, and system that depends on gas injection, especially for miscible process. So you need to work with more components. For example, if you are working with a gas condensate reservoir, maybe 5 is sufficient. Okay, for gas condensate reservoir, where you inject lean gas and produce the wet gas, the condensate gas. So you can use the cycling process to inject this. You can produce the wet gas, remove the condensate, and inject the dry gas back to your reservoir. This is called the cycling or recycling process. This kind of recovery method can be represented with 5 or 6 CO2 components accurately. However, if you are working with an oil reservoir, injecting gas, CO2 or CO2-rich mixture of gas to produce and to generate a miscible flooding in your reservoir, you should include more components in your representation. So we typically use 8 components in our models to represent the interactions between the CO2 injection stream, and the oil in the reservoir. Okay, so 8, I would say it's recommended for miscible process. Okay, it's a good strategy. Some authors recommend more components. I think 15 is too exaggerated. I think we should be impossible to run a field scale model using 15 components in our representations. It will be very hard to run this model. Think about to build a matrix with 15 equations, more equilibrium equations, solving for more than 1 million grid blocks in your model over the course of 40 years. So I think it's impossible to run this model with this number of components combined with a huge number of grid blocks over a long schedule. So we need to be practical. We need to think in a practical way. And one thing is to reduce the numbers. So to reduce the numbers, like an upscaling process applied to fluid characterization. So fluid is part of your upscaling process. Upscale is not only dedicated to rock properties. I think we should include and should think how the fluid representation should be used in a field scale representation. So it's part of the game to reduce the number. Maybe 9 or 8 can be used for practical applications. Okay, so we need to be practical, especially when you are dealing with big models, field scale models. Everything depends on your scale of representation. For small models, if you are trying to, for example, to simulate a sling tube test, sling tube is a test to measure the minimum miscibility pressure, and you can run a 1D model in a compositional model to represent and to simulate this process numerically. So it's very practical to calibrate. It's one way to calibrate the minimum miscibility pressure, measuring the depth, and see if the fluid model can match this minimum miscibility pressure. One way to do this is to simulate this sling tube in GEM or in another numerical simulation. And to do this, you need to work with more components. So 9 and 8 component is recommended to do this step, okay? So let's go to the practice number 2. The first is from the same paper, from Coral Coates paper. Okay, there are several fluid data available in this paper. I I took this one, it's for gas, a gas mixture. Okay, take a look at the methane amounts. Most of the mixture is made up by methane. 70% of my mixture is methane, so it's the key component for us. And we have a few amount of C7 plus. Okay, a small amount of C7 plus. In this case, I have a CVE. This is the composition analysis for this pressure. This pressure is the saturation pressure, as you can see here. Okay, this pressure is the saturation pressure. This guy, it's not bubble pressure, it's dew pressure. We have the variation of the volume, and you have the Z factor for this gas. Okay? We have a separator test as well. The GOR is much higher than the previous GOR because in that case it was oil mixture. In this case, it's a gaseous mixture. So the idea is to input this data in prop, test the EOS prediction with the default coefficient. We now already know that it's not possible to predict accurately. These lab data use the default parameters. We can test this again, use this other fluid data. So it requires us to tune the EOS parameters in order to fit the lab data. But before following to the regression, let's lump the component first. I want to show you how you can lump the components using WinProp, and after that we can tune the equation of state parameters and make our regression. Okay, let's go to the WinProp. Now I think the key point is to use the main monitor to project. The other monitor is not working. So let me open the practice number 2. Okay, it was the practice that I sent you before the class. This practice has all the data from the experiment that I just shown you. Okay, it's a gas case. I just picked the Peng-Robinson, the latest version of Peng-Robinson to use. I set this unit, PSI and degrees Fahrenheit, and I will feed the composition in molar fractions. Okay. I already included all the components that I have in my mixture. Take a look here. Those are the components in this mixture. Okay, I have CO2 from CO2 to C7 plus. They are here, CO2 from C7 plus. I input the primary composition of this mixture. Okay, I just copy this table. Okay, just copy this column to WinProp and paste here. The saturation pressure in this case is a dew pressure because it's a gas mixture. Include the atmospheric pressure is 4,856 psi. Okay, in absolute pressure. I include a CCE, a constant composition expansion, and I have two pieces of data from this lab experiment. I have the relative volume and the gas viscosity. Okay, in this case, I have the gas viscosity measured by the experiment. The gas viscosity. Where is the gas viscosity? I think I forgot to paste the gas viscosity here.
I think you have pasted the gas viscosity with the gas Z factor in gas viscosity.
Oh, okay. Oh, thank you. So thank you. Okay, I need to. Okay, thank you. Yeah, this is the Z factor. Okay. Thank you. Thanks, Sada. Great. And the separator. the separator, I have one single step of separation. So I included the pressure, the separation pressure, including the atmospheric pressure and the temperature. And in the second tab, I included the GOR and the API of the condensate. Okay, very light oil because it's a condensate. So we can test the prediction of the equation of state just to see how the equation of state will behave with default coefficients. Remember, just save and run, just to see the comparison between the equation of state. For gas, is simpler to predict because the equation of state are tuned for gas mixture. So the prediction it seems better than for oil or lake mixture. But we can double check the summary, the table summary later. Let me see what more I have. This is the gas. There is a deviation between the data and the prediction for the gas. And that's it. I just have this data and this data for the CCE. If you want to see the prediction for the separator, you have to go to the summary table. Okay, go to simulation output. Go to the second tab. Go down and try to find. Oh no, I'm not. Oh, sorry. I don't have the table in this case because I'm not running the regression yet. But I have the prediction here. I can check here in this table. This last table is the separation calculation. So this is the separation calculations equivalent to this keyword. So this keyword generates this output for us. So I put this composition analysis, and for the pressure separation and for the temperature, I generated this prediction. So take a look. This is the saturation pressure predicted by the equation of state using default parameters. This is the separation pressure that I put in my project, and this is the atmospheric pressure. Okay, so for this condition, I generate a total GOR of 8,300. The data that I put was 8,900. So there is a deviation between the prediction and the let's double check the API as well. They compute the API. API is here. Oh, API is, oh, it's too bad. Okay, the API is 41. I think I put 41, 49, and here is 63. So there is a big error related to the API. We need to improve this prediction. This prediction is not accurate to follow through. Okay, we need to solve this. But before doing the regression, I want to do one step first. I want to do the lumping. Okay, to do the lumping, you can click on composition. There is a button here. Is the component lumping. You can click here. Okay. And here you can set your lumping scheme. You can define your lumping scheme. For example, let's keep CO2 as a separate component. Okay, let's assume that this is a gas depleted reservoir, and I intend to inject CO2 for storage in this reservoir. So as part of my plan to increase the amount of CO2 in the porous media. So the CO2 should be represented as a separate component in this case. So let's keep CO2 as a separate component because I'm planning to use this as a site to store CO2. And the other component, maybe I can lamp. Let's put a big number here. Okay, the component 1 will be CO2. the component number 2 will be the lump between nitrogen and methane. Okay. Let's create a lumping. Let's try to do like a very simplified case, lumping C2, C3, C4, C5, and C6. And C7 plus, let's keep as a separate lump. Okay. Let's try to work with 4 components just to see if we can match the lab data with 4 components. So this, let's save this as another name. Called B. Okay. So here I just create my strategy, but I need to run this case. I need to run this case in order to process this lumping. So I just recommend WinProp to follow this strategy, to create this strategy. Okay. Now I need to save and run this case. Okay. And to process the lumping, you need to go File and update the file. Okay. Update, yes. Now, if you take a look at the compositional section, now you have only 4 components. So you reduce it from 9 components or 10 components to 4 components, following the strategy, the scheme, the lumping scheme that you set in the previous step. Okay, you can save. If you want to preserve the previous step, you can save this as another name, because remember, there is no undo button in WinProp. I do recommend you to save every step as a separate file. Okay? So now you have 4 components. You don't need more this keyword. You can cut or delete this. So you already have your 4 components. And all the properties for those components were calculated using mixing rules. So some of those mixing rules are presented in this slide. So this slide summarizes how WinProp compute the equivalent PC, TC, and eccentric factor for the pseudo component created after the lumping. Okay, this is the way how the WinProp can handle this lumping process. And now we can do our regression following the same steps. After composition, we can call the regression button. So this is the start regression button. We can click on composition and call the strategy regression parameter. Remember, we need to include all the experiments, the lab experiment, inside the regression block. One smart way to do this, go to the model operation, pick the experiment that we are planning to copy and paste. Okay, I will use cut. Okay, yes. With the right button in your mouse, you can paste into the reg block. So now the experiments are submitted inside the regression parameter block. Now we need to follow the same steps. We need to pick the components that the parameters that we will tune. Okay, let's take 2 critical parameters: eccentric factor, molecular weight, and volume shift. And remember, let's select this correlation, the correlation that controls the binary interaction parameters among the components. So let's use this correlation and let's regress on this correlation in order to get the match between the prediction and the lab experiments. Let's start with the weight number of 1. Okay, let's use 1 as a default weight. if we need to put more weight on a specific property, we can operate later, okay? But let's start with one. Save and run. We can see the graphs. I like to see the summary plots. Oh, it seems much better than before. Before is represented by the green curve, and now the final curve is in red. This is the relative volume of the gas, okay? The dots are the lab experiment. Another data that we have for the gas, for the CCE, is the Z factor. It seems better. There is a deviation. We can double check the error associated to this deviation. We can tolerate, let's double check our table. You don't need to memorize, you just need to check the right place. Let's double check the Z. The accuracy is between 1 and 3, okay? The accuracy for the Z factor is between 1 and 3. So we need to go to the table and see if the error associated to these properties is lower than 3%, okay? If it's lower than 3%, we can consider that the prediction can fit the lab experiment. Let's double check. Let's go to the table. Alt file, go down. Where is the table? Over here. Over here. The saturation pressure. The tolerance is 5 bars, okay, 5 bars. 5 bars is more than 60 psi. Yeah, it's almost good. Almost good. It's not almost. Maybe you can improve the saturation pressure. Maybe you can add a weight greater than 1 for the saturation pressure, just to improve the matching of the saturation pressure, because it's very important property for us, because it controls all the phase behavior in the project. For relative volume, I think we got good results, okay, because the tolerance is around 1 and 2%. We are lower than this. We don't have viscosity. And for Z, take a look. That deviation, it looks a big deviation, but in terms of error, the deviation is lower than 3%. So you can, in other words, you can consider this as matched. Okay, I think the separation pressure for GOR we have 1% of error, and for API, take a look. This is very interesting, because the lab data is 49 degrees. The initial prediction is 61, too high, and now we could reduce the prediction to 59, almost 49, almost 50. Okay, so now the data is matched. Okay, so I think the only thing that I would do here is to increase. Let's try to run with a weight of 2 for saturation pressure. Let's go back to the output file and see now the error is lower than before. Yeah, now I have only 50. Yeah, I think the difference between this number is the experimental number, and this number is the regression after the tuning. The difference is lower, is around 50 psi. So 50 psi is lower than 5 bars. Okay, so 5 bars is the tolerance for the saturation pressure, as we said yesterday. Okay, so this number can be considered the match. So we are done for saturation pressure. We are done for relative volume, because all the values from this column are lower than 1%. It's very good, very accurate. We don't have viscosity data to match, okay? So I will skip this part, and I will take a look in the z-factor. So the z-factor, it should be lower than 3%. Most of the values are lower than 3%. So I think we can go ahead and consider this matched. The separator data is very good. Okay, the GOR is around 1% of error, and the API is lower than 1%. I think we are done for this gas. So the next, so this.
But there are some Z value that above 12%, the last values before Z table.
Yeah, good point, Professor. Yeah, but take a look at the pressure. The level of pressure is very low in this case. Probably I will operate at lower pressure, at a higher pressure. Okay, so very good point, Professor. Thank you for highlighting this. Important to point out that at lower pressure, I don't. It's not my I'm more concerned about higher pressure. Okay, higher pressure, because it's the operational pressure. Those are the operational pressure to operate the reservoir. At lower pressure, probably I will not operate this reservoir. So we need to be more strict with the higher pressure, okay? Or the operational pressure for the reservoir. Okay? So we can tolerate this error because this is very low. So I can conclude that this lumping strategy worked. So I can use this for numerical simulation. So this is my conclusion. So need to go, we can update again. We can save with another name. We can disable our regression parameter, and we can export the file for gem. So click on composition, click on the gem button here. You need to input temperature. So to input the temperature, you can click on this second button. I will use this temperature to 67. I'm assuming that this temperature is representative for the reservoir. Save and run. If you go to File, go to View Gem EOS Model, and here you have the file to be used in GEM. Just copy and paste in your GEM model. So you have the equation of state of Peng-Hobson, represented by 4 pseudo components, CO2 and 3 hydrocarbon components. Okay, the properties of the components are here, and the matrix of binary interaction factor parameters are here. Okay, and the viscosity. In this case, we didn't match viscosity data because it was not available, but I assume that we can rely on the viscosity computed by the default parameters of this correlation. For gas, we can rely on the default parameters. For oil, sometimes is more complicated, but for gas, let me, what I did. No, I think sorry. For gas, you are still looking at my gem model, my gem output file.
Yes.
Yes.
Great. I'm a little bit puzzled with my 2 screens today because I'm working from the office today and I'm not using my personal computer today, so I'm a little bit confused. Okay, so I was talking that in this case I think we can rely on the default parameters because we are dealing with a gas mixture. Okay, so I think we are done for this exercise. Any question about this exercise?
Dr. Marcos, I mean, this is fine that we can like explore the gem model from WinProp, but what in case if we are accessing the WinProp from Builder? Like some of the cases where we have the equation of the state and then we are updating some properties in the Builder, and we have the WinProp on the other side, like, and we update it, and then we just like once we update it, it doesn't update the Builder directly, right?
Yeah, the approach is very similar. You can open your, if you already have a gem model built, you can open this model in Builder, and from Builder you can launch WinProp.
Yeah.
So you can do the same thing. So you cannot launch Builder from WinProp, but from Builder you can launch WinProp, and WinProp will open with the numerical, with the component properties from your numerical model. So Builder is able to launch WinProp and load all the properties included in your WinProp include file. Okay.
But what we if we change the WinProp model, like for example, this is my WinProp model, and I opened it from Builder, and I'm changing this WinProp model now. And when I'm saving it, it doesn't update my Builder model.
No. You need to generate a new file and update manually. Yeah. Okay. There's no automatically. It's not automatic update between the two platforms.
Okay.
Unfortunately, not yet. Okay. They are not smart enough yet. Okay. Let's go back to the presentation to guide us. Let me put in the. Let me use this primary monitor. Okay. Let me recover this. So we stopped at this slide. Okay. The next topic that I want to cover is about gas. Now, my plan is to talk only about gas from now onward. Okay. So the gas is important for us because we need to match density for the gas, and to match density, we will operate on the equation of state calibration, as we did for oil and for the gas mixture. Okay, equation of state is the tool that we have to match density data. Okay, and density is important for us because density controls the buoyancy. So buoyancy is part of is important and relevant for CCS and hydrogen projects. So you need to, we are injecting a gas, and this gas will go up throughout the porous media. So it's very important that your density is accurately calibrated with the lab data that it represents that mixture. Okay. Another important parameter for the gas is the gas viscosity. So we can use a JST correlation as we did for the oil mixture. We can do the same for the gas. And viscosity is relevant because viscosity controls the injectivity and the mobility in the porous media. So both mechanisms are present during a CCS, are playing a very relevant role during a CCS project or during an underground hydrogen project. So we need to be careful about how to represent the viscosity at reservoir conditions. And I think the novelty for this part is the solubility data. So especially for CO2, where the affinity between the CO2 and the water or brine, part of the CO2 can go into the aqueous solution. So you need to compute this amount, that this phase change between from the gas phase or supercritical phase to the aqueous phase. Okay, and for that you need a solubility model. And this solubility model depends on some parameters of the equation of state. So this explains why I recommend to do this step only after calibrating the equation of state. So starting calibration of your equation of state. After that, calibrate your viscosity model, because the viscosity model, especially Petersen model, uses some parameters from the equation of state. And the later step is the solubility model calculation. Okay, you can perform this step as the final step in your fluid modeling or in your fluid simulation. And this is important because the solution, the gas, is one of the trapping mechanism, especially for CO2. For hydrogen, can play a less relevant role, but I think in some cases important to consider if you are working with low salinity brine, maybe the amount of hydrogen trapped in this brine. If you are concerned about geochemical reactions, so the hydrogen in the aqueous phase can react with the primary minerals of the rock, can react with other gas. So this part should be in the aqueous phase. So it's important to model how much of your hydrogen can go into the aqueous phase in order to represent the geochemistry between the hydrogen in the aqueous phase and the minerals or other gas. And at the final result for this process is the final model. So at the end of the day, you will get the equation of state calibrated, the correlation for viscosity calibrated, and the final solubility model calibrated as well. Okay. These slides from our paper. Okay, we applied this workflow for density, viscosity, and solubility calculation, trying to overcome some difficulties in calibrating at the same time, simultaneously, pure hydrogen data and mixture with different amounts of hydrogen. So the challenge is to combine, using the same strategy, using the same correlation, accurate prediction for pure hydrogen, 100% of hydrogen at reservoir conditions, with the prediction for viscosity of mixture of several different amounts of hydrogen. So this mixture is between hydrogen and methane, I think so. I need to double check, but the relevant point here to highlight is the amount of hydrogen is variable. So you have data for 20% of hydrogen in the mixture, 50% of hydrogen in the mixture, and 80% of hydrogen in the mixture. And sometimes it's very hard to combine both fittings, because you can fit the mixture, but you cannot fit the pure component. So the challenge is to combine those to get both fittings at the same time, at the same viscosity model. We did this performing this methodology that I explained last class. For density, we used volume shift to calibrate the density. Actually, the density is very well predicted using default parameters. Sometimes you need to correct some deviation, especially at higher pressure. There's, for some mixture, we can observe some deviation, especially for hydrogen. You can observe some deviations at higher pressure, and you need to fix this deviation. To do this, we tune the volume shift. The volume shift, remember, is the third parameter in the equation of state. It's the parameter that was created to fix the density correction. So it's very useful to do the same. It was created for liquid, but you can use the same strategy for gas mixture. Okay. For viscosity, we use the JST model. And for solubility, we used this model available in WinProp and also available in GEM. So it's the Lee and Yan model. Is convenient model because this model is available in both simulators. So you can calibrate it in GEM, in WinProp, and export the final parameters to be used in a GEM simulation. There are other models, more sophisticated models to represent solubility. However, most of these models are not available in GEM. Some of them are available in WinProp, so you can use in WinProp, you can calibrate them in WinProp, but you don't have the output to input in GEM. So in a practical way, you don't have what to do with this model. The best way to handle this limitation is to work with a model that is available in both packages. So Lee and Neil was a practical decision because this model is flexible. It has two parameters that you can calibrate. One of these parameters, the Henry constant, the popular Henry constant that it was formulated to model solubility in pure water, and the molar volume at the infinite dilution. So we have two parameters. We can tune both parameters using the same methodology that you used for the viscosity parameters in the viscosity correlation. And after this, after conducting three-step regression, we can export the final model. Okay. I will show you some results just to show you that it's possible to succeed applying this workflow for gas. For example, for density, our goal is to get a match with less than 1% of error. Okay, so I'm comparing the pure components. This is the same equation of state. It's important to point out that all those slides all those graphs were obtained using the same equation of states. Only one equation of state that was calibrated, and this equation of state has the capability to represent all those compositions, okay, different compositions. So it's very practical to get this broad representation because you can use the same equation of state for simulating different conditions. If you want to simulate a gas rich in methane and you want to inject hydrogen in this reservoir to store hydrogen, so you need to be predictive for methane and for hydrogen using the same equation. Okay, so it's very important to match methane because methane is the native component in your reservoir, but it's very relevant to be predictive for hydrogen as well because you are planning to inject hydrogen and to store hydrogen in that reservoir. So the equation of state should be able to match the properties for both components. So as you can see, it's possible. You can match density, and density is important to control the buoyancy effect in porous media. So for methane is predictive. All these graphs has less than 1%. For hydrogen, at 60 degrees C, at 125 degrees C, okay, is predictive. You can see some deviation. Take a look here. You can see some deviation at higher pressure. The pressure is very high in this case, okay, it's in kPa. It's very high. So in this, take a look here, the pressure here is still high, but there is no variation before and after the regression. In this case, there is for methane is predictive, but for hydrogen, it's important to it's worth nothing that for hydrogen you face some deviation at higher pressure. Take a look at here. For hydrogen, there is some deviation, and this deviation was fixed with the regression. The red line represents after the regression. Okay. When the pressure is higher, the deviation increases. So it highlights how relevant it is to perform this correction in the equation of state. Okay, and
Marcos,
yeah, sure.
in case of depleted gas reservoirs, like in my case, we have 100% methane, right? For example, and we are injecting hydrogen. So we need to just like take care of 100% methane and 100% hydrogen.
Yeah, but in this case, in the reservoir, there will be a mixture, okay, of hydrogen and methane. So it's not only you need to be predictive for pure components. However, need to be predictive as well for mixture. So in this part of the slide, the lower part of the slide, you can see that the same equation of state was able to predict mixture property as well. So, for example, if in your reservoir, you can have a mixture of half and half of hydrogen and methane. So it's possible to predict. 20% of hydrogen, it's possible to predict. CO2, what happens if you add CO2 in the mixture? It's still possible to predict. Okay, so even ternary binary mixture you can predict, and mixture with three components was still possible to predict. We can test more, but we need data. The test is limited by the availability of data in the paper. So we gathered several data available in different papers, and you try to include all of them in this test. Okay.
What in case of like saline aquifers when we are having, for example, CO2 as a cushion gas, and we are injecting hydrogen? Then we need to do like for 100% CO2, 100% hydrogen, and then mixture of CO2 and hydrogen.
Yeah, you have to do for CO. Actually, we did for CO2, but it's not plotted here. But in the paper, the same equation of state is predictive for 100% of CO2 as well.
Oh, yeah.
You are right. You're right. Okay. So it's for density, it's very simple. I think the main method is for density. It's very simple to match and to predict. Only small deviations might be fixed. Only small variations at higher pressure. The challenge is for viscosity. Okay, viscosity. So this is the main tool used to get this matching was the volume shift. So we basically tuned the volume shifter in order to get that matching. Okay, this is the tuned, the final volume shift. It was applied for the three components. So we did for hydrogen, methane, and CO2. The default parameter is 0. So the difference is the change in relation to default parameters. And according to Peterson, this change is agreement with the tolerance. So she recommends a range of variation more or less 100% is allowed, according to Professor Peterson. Okay. For viscosity, it's more challenging. So for viscosity, to combine different compositions at different pressures and temperatures, we pick JST to do this, because JST, as we discussed the last class, is much more flexible than Peterson because you have more parameters involved. So your degree of freedom is higher. So you can try to better optimize those parameters to fit the lab data. So you have different conditions, different mixtures, and some mixtures had better results than others. For example, this is very good for CO2. 100% CO2 is very predictive. There is a deviation here for half and half CO2 and methane. the bigger deviations are related to higher high temperature samples, but higher temperature samples not representative for us. For example, 400 degrees C. 400 degrees C, I have never seen a reservoir with this temperature. So for me, it's not representative. So I reduce the weight for this sample in my regression parameter. You can use this practical feelings about the representative temperature, the representative pressure for your case to give you a criteria to set your weight. For example, for this sample, I put a very small weight because I consider the other samples much more representative than this. Another case, take a look at this mixture, 7 degrees C. 7 degrees C for reservoir conditions, not representative. Can be representative for the production guy, but our focus is on the reservoir. So our focus is to model the flow in porous media, to model the flow in the wellbore, and that's it. So for this mixture, the deviation is higher than in the other case. Take a look here. Let me magnify here. Take a look. There is a deviation. The correlation was not able to fit the lab data, the orange dots here. However, take a look. 7 degrees here. Why I used this data? Because it was I just have this data with 3 components. It's very rare and hard to find representative data when you are dealing with more components in your mixture. For pure components, you have a NIST database, so you can take CO2, nitrogen, and methane in several different temperatures and pressures. For binary mixtures, you have some papers, and we build with Dr. Mohammed Hotan an Excel spreadsheet gathering this data. But for 3 component system, it's very hard to find this data. Okay, but I consider that we succeed in doing this. Okay, this is the deviation in terms of error. Okay, the simulation prediction minus the experimental data. Okay, the deviation, and take a look. The higher deviations are related to the samples with 400 degrees C and 700 degrees C. Okay? And for gas, the accuracy is around 6%. So for pure components, 2%, and for mixture, till 6% can be considered accurate. Okay. So this practice, I recommend you to do as a homework. Okay, this practice is trying to do the same that we did in the paper. Okay, in this practice, I'm using all the data that we gathered during this study. Okay, during this work, there are broad composition. A broad composition including pure hydrogen, pure CO2, pure methane, and mixtures. Most of them are binary mixtures. You have density data and viscosity data. So I do recommend you to do in 2 steps. First, match the equation of state using the volume shift to match the lab data. And after that, you can match the viscosity data. Okay. Let me show you this example. Let me close this. Let me open the practice tree. practice 3 is your homework. Take a look. The project is much bigger than the previous one because you have much more data available. This is very close to a real case because in a company, in an actual project that we often work in a company, we have to work with multiple samples at the same time in a semi-project. So this case is very close that I'm using it to work normally. Okay. Take a look here. I'm using only the volume shift to match the data. Only the volume shift. Why? Because those components are pure components. And remember, for pure components, don't regress on the parameters for pure components. We discussed about it. Okay. Don't change the components, the properties for pure components. I change only the volume shift because the volume shift was done to calibrate the density, and the density is the deviation that you want to fix. Okay, is the source of deviation that I want to fix. So that's the reason why I pick only the volume shift as the regression parameter for this example. And only doing this, I was able to calibrate. I could calibrate all the data that I presented to you. Okay. So I will skip this project. This is for your homework. You can do this for the gas phase, the gas mixture. And my plan for now is to discuss about solubilities. Our last topic to cover is to discuss about solubility and how to fit solubility data, especially for CO2. But you can do the same and follow the same steps for hydrogen. Okay. Just to give you a brief introduction about the solubility. I'm not going into detail on this topic, just to give you that I want to represent, for example, the CO2 in aqueous phase. So I inject CO2 in gas phase or supercritical phase, and depending on the pressure, temperature, and the brine salinity, part of the CO2 can go into the aqueous phase. Okay, my goal is to compute this amount in aqueous phase. I can do this using equality of fugacity, okay, where the fugacity of the gas phase, the gas phase, the CO2 in this case, can be calculated from the equation of state. It highlights why it's relevant to calibrate the equation of state beforehand. Okay, it highlights why I need to calibrate first the equation of state before going through this topic. Okay. And the fugacity of the component in the aqueous phase is calculated by Henry's law. And the Henry's law, I can input the Henry's constant. The Henry's law constant is a function of pressure, temperature, and salinity. So this coefficient will control the dependence on pressure, temperature, and salinity. Okay, and remember, if you increase the pressure, you will increase the solubility. If you increase the temperature and salinity, the relationship is negative. You will decrease the solubility. Okay, it's a positive relationship with the pressure and negative relationship with the temperature and salinity. The convenience for us is we can use the same model in WinProp and GEM. So you can calibrate Lee and NIA model available in both softwares. This model can be used for several hydrocarbon components and non-hydrocarbon components such as nitrogen, CO2, and H2S, and hydrogen, and pure hydrogen. You can use the same strategy, export the parameters. Basically, this model will generate three key parameters for us. The Henry's law constant is the first parameter. The the partial molar volume and a reference pressure. It's just a pressure because you need to calibrate for a pressure, and you can correct to other pressure using this calculation. Okay, you export this constant is valid for this pressure, but as pressure is a variable very important in our simulations, because pressure is our operational variable for a recovery project or for a storage project. We don't control temperature, but we can control pressure because you are injecting fluid, you are producing fluid in a recovery project. So pressure is our operational variable for us. So it's very important to update the Henry's constant as a function of pressure. One way to do this is using this equation. So this model uses this equation that updates the.
I have a question.
Okay. This pressure, the P star, is the pressure that comes from improp, and P is the pressure in jam, in our model, numerical model. Okay. The H star comes from improp, which was calibrated for the P stars, and in jam, for jam simulator, jam we will use this up to date on the new conditions that you want to simulate your process. Okay, is it clear?
Yeah, just a little confusion about it. So really, like, we calibrated the solubility in WinProp. Now we have this calibrated Henry constants from WinProp. Now when we will be inputting it in the jam, so we'll be inputting it as the reference pressure of the experiment, right? And then jam is gonna automatically update based on the current pressure conditions.
Yes, that's it. The jam will update as a function of pressure, but jam does not update as a function of temperature. Okay, temperature should be the same from improp. Okay. If you need to update the temperature, if the temperature is different from the temperature that you calibrate your data, you can use the Harvey's correlation. So the Harvey's correlation is available in jam, and they can be used to calibrate, to update the Henry's constant for different temperatures. Okay, so if you have a temperature very different of the temperature that you calibrated your data in WinProp, you can fix this limitation using this constant. This is the keyword in jam. Just Henry / core / the CO2. It's available for some gas. It's available for CO2, nitrogen, H2S, and C1. Okay, the equations are here. Basically, which changes are the coefficients of the difference between the gas are represented by the coefficients here. Okay. Another effect that's not considered in the WinProp is the salinity effect. So if you want to consider the salt out effect, this is important when you are working with dynamic salinity in jam. If your salinities change over the course of your simulation. For example, if you are working with a geochemical reactions. So in this case, you can generate more salt, so you can generate more ions that can affect the initial value of your salinity. In this case, you need to update the Henry's constant because your concentration of salt is changed over the time. One way to do this is using this equation, this Kramer equation that is available in jam. Okay? This is the equation that it used, that's a version for CO2 and another version for methane. Just to show you that's possible to represent the solubility for hydrogen. Okay, I picked this data from this book. This data is the hydrogen solution in water, in pure water. Okay, and I compare the solubility predicted by the Lee and Neal model at 50 degrees C using the default parameters. I just simulate using default parameters for water. I just changed the temperature and the pressure, and I got this green curve. Okay, and there is a deviation. Take a look. The solubility is very low, very small. But after some regression steps, I could calibrate the prediction with the lab data. Okay, I got new data for brine for 2 levels of salinity. This is a low salinity brine, 60,000 ppm. This is a very high salinity brine, almost 200,000 ppm brine. The temperatures are different because the data are different, were obtained from different authors. I compare again the prediction before and after the regression. So in both cases, we could calibrate the data using the 2 parameters available in the model, the partial volume and the unhinged constant. Only with these 2 parameters in the volume, we could calibrate data to represent the solubility of hydrogen in the brine. So we can conclude that we can calibrate this model for pure water, and for brines. For CO2 is the same thing. The same model. We gathered data from different papers for CO2 at different conditions for pure water, for different levels of salinity in brine. In this case, low salinity brine. In this case, high salinity brine, very high in this case. And take a look at low salinity brine. The model has a very good prediction using the default parameters. The difference between the curves is very small. So basically, there is no practical decision. There is no difference here. The difference is very small. However, when you are working with high salinity brines, you need to take care. You need to be careful because high deviation can be observed, especially at higher pressure, for the prediction using default parameters and the prediction after the regression. So the regression in this case is mandatory. You have to regress on the solubility model to fit the lab data. And another point, compare the scales. Take a look at the values. Compare the values for CO2 with the values for hydrogen. Take a look at the difference. The solubility for hydrogen is too small, as I have commented before. Okay, take a look. For hydrogen, is a less relevant mechanism. It's relevant if you are trying to represent reactions, geochemical reactions. But for CO2, it's mandatory. You have to include, even for high salinity, you have to include in your model the capability of CO2 goes into the aqueous phase. Okay, and take care, be careful at higher salinity pressure, because if you are using this model, the Lee and Neal model, you have to fix this. I didn't test for other models. There are a bunch of models for solubility available in commercial or other commercial simulators, but I would say that maybe you should do the same thing. I think we need to. The models are mostly calibrated for lower or mid salinity brine. For high salinity brine, as you can, for high salinity brine, it's very common in Middle East. It's very common in Brazil. So In Canada, Quest, the famous project operated by Shell in Canada, the CCS project, the Quest project, the brine salinity is around 300,000 ppm, 300,000 ppm. So if you are dealing with this level of salinity, or around 200,000 ppm, take a look at this and regress on the default parameters, because you need to fix this deviation. Okay, and you can do the paper we discussed that it's possible to do using this coupling between improper and jam. And this is the practice for you. This is the practice that I want to do with you. We have this data. This is the data measured by. It was not measured by these authors. They only use the data measured by other authors, but I used the paper just to pick some lab data to use with you guys. Okay, so this is the solubility of hydrogen in a brine with 1 molar of salinity. Okay, it's not a high brine salinity. A high salinity brine. It's not a high salinity brine, but it's a brine. It's not pure water. So the idea is to input the data to show you how to input solubility data in WinProp, how we can pick the two parameters of Lee and Nian model, the partial volume and his constant, how to tune those parameters and export the final parameters. Okay. Let's go back to WinProp. Can you see my screen?
Yes.
Yes.
Thank you. Because now I'm using only one screen, I cannot see you. So if you lose my screen, let me know. Okay. I will open the WinProp. Okay. Let's go to practice 4. Let me show you one thing. In the practice 4, we have a column of pressure. You have from 1 bar to 250 bars. So each value is for this bar. So as I commented with you, the solubility is a function of pressure. So you have one value for each bar. And it's a function of temperature. So the columns represent the temperature. So I will pick this one. I will pick only this column to fit. Okay, it's 353 Kelvin. It's around 8 degrees C, 80 degrees C. Okay, 80 degrees C. So I will pick this one to fit. Okay. I'm assuming that this temperature is representative for my aquifer. So that's the possible reason to select this to work. Okay, so we need to pick the equation of state. We need to pick the units. In this case, my units are in KPI. It's not in KPI, it's in bar, but it's convenient bar. Is basically cut 2 zeros and convert, or put 2 additional zeros. It's very easy to convert from bars to KPI. So I pick I don't have bars as one of the options available. So I pick this because it's more convenient for me. I need the component. In this case, I have only water and hydrogen in my mixture. Okay, I have only 2 components in my mixture, water and hydrogen. So I insert both in my model. I'm using the linear model. I'm using this here, linear model. Okay, just fourth tab, I pick linear method to work. Using the composition, I'm using the primary compositional is the in situ compositional. My native fluid is water, so the primary is 100% of water, and my plan is to inject 100% of hydrogen. Okay, the secondary stream is the stream that you are planning to inject in the porous medium. The primary is the in situ fluid or in situ component in your porous medium.
Marcos?
Yes, sir.
In the component selection or property section, when we selected the Henry's law constant correlation, we see like the aqueous salinity is 0 in this case. So, like for example, we have solubility data for salinity like 1000 ppm or something. So we need to input here, right?
Yes and no. You can use the salinity here if you want to rely on the default parameters. For example, if you want to see the value for example, I can put here that is small per kilograms of water is 1. I can put, but these values used only when you are working with the default parameter. If you want to generate a prediction, use the default parameters of the correlation. They use this as an input for the model. If you are regressing on the parameters, you don't need to input here.
Okay. Because it has already the impact of salinity in the calculation, I mean the variables. We don't need to regress it. We are just matching the equation of the state.
Yeah. In this case, we don't because we can do two things. We can generate, for example, another project. Let's do from scratch. Let's pick the same units. Let's select the component. It was hydrogen and water and hydrogen. Okay. And let's see. Let's run the model using the default parameters without regress on the parameters. Okay. We need to include 1 for our in situ component and 1 for our injected component. We can export a gem model. This is for export gem model. We can use the temperature is 80. The temperature is 80. And here there is a field for solubility parameters. We can click on here. Okay. We can pick. We can set the solubility parameters at 80 degrees C, and let's see one pressure. Let me see the example. 200 bars. That's 200 bars. 200 bars is 20,000 kPa. Okay. So we can run this example. Let's say with another name. I will call this default solubility. Okay. We can save and run this case. We can go to File, View EOS Model, and you can get here. Oh, there is not calculated, not computed. What's going on? Let me see.
I think it's the weight fraction is 1.
Oh, I forgot to do something. I forgot to set here. I need to calculate the aqueous component. I need to put 80 and 200. Okay. So better, let's, I think it's default. Let's put default, because default we will use these settings here. Now we can save, run, and run again. Let's go back to file. Yeah, oh no, not yet. What's going on?
Marcos,
Yes.
you're putting the unit is weight fraction. It's not about this because you put 1, so there is only salt in the composition.
Oh, thank you, Rodrigo. Oh, thank you, yeah. Thank you. It's molality, right? Yeah, now we got, thank you, Rodrigo. Now we got the coefficients for the solubility model. The first one is the Henry's constant. This is the reference pressure. This is the 200 bars, okay? This is the partial volume. But this is for one molality of 1, okay? Molality of 1. Without calibrate the model. This is the default model generated by the model. But I'm not sure if this number is accurate or not to represent this the experimental data. One way to do this, it was we did in the paper. The paper was just this comparison. We run the model without any regression steps, and after the regression steps, and compare and see this deviation. Okay, we can do the same. You can run the model without any calibration. This is the goal for this part of the exercise. Just run the model and generate the default parameters. And now we can try to find some data with molality of 1 to regress on that. So this is the goal of this part. So this practice 4, we got some data to regress. In this case, to regress, we don't need to include the concentration, because the effect of the salt is included in the data. The idea is the solubility that is set in this field already has the effect of the salinity on that. So the effect of the salinity is included in this value. So we don't need to include the salinity effect here, because I will skip this part and I will rely on this number to calibrate the model. So I set the experimental data, and I will allow this number to overcome the default parameter in order to calibrate this model. So the calculation is done by this step. Let me show you. The calculations here is different. It's not clear in WinProp. It's a little bit hidden when you compare to the other lab experiments. All the lab experiments are in this part. Okay.
Dr. Marcus.
Sure.
I have a question. So,
sure.
Again, for the salinity, what if the solubility data you have is for a certain salinity, but you want to calibrate AUS for some different salinity. What do we do in that situation?
No, actually, I don't have a solution for your question, because the only thing that you have available is to regress on a only salinity, a single salinity.
Yeah.
You don't have how to regress on other salinity. The parameters are fixed for a specific salinity.
Yes.
So my recommendation for you is to pick the salinity more representative for your case, pick a data that represents that salinity or is close enough to that salinity, and regress on that data, to calibrate that data.
Okay.
It's a limitation. I recognize, I acknowledge that's a limitation of the process, the modeling process. We don't have to, we use this model, okay? There are other models with more parameters that you can regress on the parameters that controls the salinity dependence. But using this model, we are limited to regress on a single set of salinity.
Okay. Thank you.
Good point. Yeah, you notice a very important limitation of this process. Okay. As you can see here, for each salinity, we have the own set of parameters. So we have different sets of parameters, each sets for a specific salinity. Is a limitation. Okay, I cannot generate equation broad enough to represent different levels of salinity, as we can did for density. For density, the idea is to have only one equation of state able to match different conditions of composition. This is my dream for solubility, but with the models available in the commercial packages, we are limited to represent each salinity at a time. Okay. So I was showing you where we can use the multi-phase flash. The multi-phase flash is not included in the lab tab. It's included in the calculation tab. Okay, in this case, water, gas, water, oil, gas, water, oil, gas, water. The first tab of this option is the pressure and temperature. It's not practical because you have to use one for each pressure of your problem. For example, we want to represent five or six pressures, six different pressures, levels of pressure. You need to use one keyword for each pressure. So the difference, that means, oh, I can't open more. So the difference among those entries are the pressure. This one is for 1 bar. This one is for 50 bars. This is for 100 bars. This one for 150 bars. So each is restricted. Each one is restricted to one pressure, okay, and one temperature. The experimental data is here in the fourth tab. The fourth tab, you can input the experimental data for your project. So I got the data measured for hydrogen, and I input here. The first one is for this pressure. This number. If I increase the pressure, I expect increase in the solubility. Take a look here. Now the number is greater than the previous number. If I work with higher pressure, like that, 200 bars, now the solubility is higher as well. So I'm using that table. I just fill it this blank using the solubility data, and we can regress using the two parameters available. Take a look. I'm not selecting any parameters from the equation of state. I'm relying on the equation of state because in this case I'm working with a pure components. It's only hydrogen in the mixture, so it's 100% hydrogen, the gas mixture. So pure components, I don't need to do anything. I need to rely on the default parameters of the equation of state. However, I have to regress on the solubility parameters. And I have only two parameters to regress: the heat constant and the volume shift, and the volume, partial volume, okay? I'm picking both. And I can save with another name, over class here. I will run the case. The graph is not good. I don't like this graph to see the results. I prefer using the table, so you can find the same table that we used in the previous exercise, just to compare if your results are good enough to represent the solubility. Take a look here. The first number is related to the water, okay? Don't consider this number for your conclusions, because this number is water. It's not affecting the regression, because -1 in prop is a new entry. It's a new entry. So it's for water. The second component, or the secondary component, is the hydrogen. So this is the experimental data for the first pressure, experimental data for the second pressure, and so on. Okay, and the solubility, the deviation of the solubility is here. It's too high. It's 14%, 17%, 17%. It's too high. The tolerance for solubility is around 2%. Let me double check here. 5%. 5% is the tolerance for this, the accuracy that we need to achieve for solubility, to represent accurately solubility data. We need to do something. However, I just have two variables, two parameters in my strategy, in my project. So I'm already using the freedom that I have to explore. But I can do something more. Take a look here. I regress on that parameters. This is the lower bound, the default lower bound of this parameter. This is the upper bound. The first parameter is the unhinged constant, and the second one is the partial volume, the lower and the upper bound. Okay, take a look. After doing this regression, the final value for this parameter achieves the upper bound, and the final value for the second parameter achieved the lower boundary. So, and I need to expand the boundaries in order to explore better the domain for both variables, with the hope to match the data. So let's try. Let me show you how to expand the boundaries. We can go to regression parameters in your project. The last tab is the regression parameters. In red, because you hit the upper parameter, and he painted in red because you hit, just to highlight for you that, oh, you are at the upper or lower parameter. So we can expand this. You can increase this number. For example, let's put 50,000, and we can try. We can do one at a time, or you can do both at the same time. Okay, let's try just to modify the first one. Let's just to expand this one. Let's save with another name. Let's save is A, case A. Let's save and run. Let's go back to the table and compare now after doing this change. Take a look. The values are still high, but they are lower than before. So we improved the quality of the regression. But I'm still hitting the lower boundary of these parameters. So I do need to modify these lower boundary. So let's go back to here and let's assume a lower value for this. Let's assume 0.01. Let's run and save and run. Let's go back there. This is still high, it's 10% of error. I need to reduce to 5. I think, yeah, I need to expand more the boundaries. Let's assume here 70,000. Let's reduce it to 0.5. Now is our trial and error. For hydrogen, I need to modify a lot because this equation was not calibrated for hydrogen. If you go back to the original paper of the author, they didn't mention hydrogen. They mentioned CO2, they mentioned hydrocarbons, gas, but they didn't mention hydrogen. And the solubility of hydrogen is too small, so we need to increase the value of Henry's constant in order to match this lab data. They will warn you because you are using higher values, but for hydrogen is needed. You need to expand. So now I think, no, it's not good. It's too, it's too high. I think I need to enhance more, to increase more, because for hydrogen has low solubility. Let's try to do this. So now it's better. Now it's better. Okay. So I think we can consider this matched because except the first pressure, but remember the first pressure is 1 bar. 1 bar is 1 atmosphere. It's not representative for the initial conditions of any reservoir or any aquifer. The most important pressure for us are the other pressures. So, and all of them are in agreement of our tolerance. So the accuracy should be lower than 5%, and all of them have an error less than 5%. It's 4% here, 3% here, 1% here. So I can consider this calibrated. Just remember, update the equation, the model, save as another name, practice B. Now you don't need the regression, you can cut. And if you want, you can export your simulation data. So you can run, and now you can export your gem model. You can go to File, View gem model, and you have the Henry's constant. And you can compare. You can go to the default solubility, and see the difference in the Henry's constant before calibration and after the calibration. So the pressure is the same, of course, because I'm using the same reference pressure just to have the same base for comparison. But the Henry's constant obtained is completely different. Take a look. The higher is the Henry's constant, the lower will be the solubility. So, and our conclusion shows that the Henry's constant obtained after the regression is 1 order of magnitude higher than the default Henry's constant. It shows, it highlights how relevant it is to perform this step. Otherwise, we would work with, we will enhance the solubility artificially. The data, the lab data, rely on the data that I share with you. The data points that the solubility is lower than the model was predicting. So this highlights how relevant it is to calibrate the model, okay? The volume, the partial volume is basically the same, the magnitude is the same, the numbers are very close, 2.3 and 2.7. But the key parameter for us is the unhinged constant, and the difference is too high. So it's very important to compare. I know that both numbers will conduct to very low solubility. The amount of hydrogen in the brine will be very low. However, if you are concerned about representing the geochemical reactions between the hydrogen in the brine and minerals or other gas, is relevant to be strict with this representation. Okay, so I do recommend you to perform this step at the beginning of your modeling process. Take a look, try to find out lab data close to your initial conditions of your brine in terms of pressure, temperature, and salinity, and do it. It's very simple. It's not complicated. I show you that you have the experiment, the numerical experiment available in prop. You can just pick the keywords and input the data and do some trial and error in order to match your lab data. Okay, so it's impactful. You can see how different are the numbers obtained using default parameters and after the regression steps. Okay, it's clear? Everyone is following me, or it's too complicated?
Just one question. Dr. Marcos, in the when we were inputting the solubility data, there was one option of like primary mole fraction of gas or primary mole fraction of water, right? So it was 0.5. So
yeah.
Is it the like standard of 0.5? So we have like 50% water and 50% hydrogen.
Yeah, it's an initial gas. Okay, we properly require you to give initial gas to try the amount of hydrogen that it can goes into the aqueous solution. Okay, just initial gas. They require you to input something, and I always use 0.5. Okay. I will take this opportunity to point out that you have other models available in prop, like dual sum model. This model is very famous for CO2 applications. It's not applicable for hydrogen, but it's very famous, so it's very predictable for CO2. However, you don't have this model in GEM yet. You don't have yet in GEM. So you can use to predict CO2 solubility in certain conditions, but you cannot calibrate this model or export this model to be used in GEM. So it's available here, it's very famous. People that are used to working with CO2 should be familiar with this model. However, I'm not using because I cannot use in GEM. I know that you guys are concerned in doing numerical simulations using GEM, intersect. So I focus the course only on NEO model because this model is more popular in commercial simulators. Okay. The last slide. I'm running over time, sorry for that, but this is the last slide, is another homework. Is do the same thing, but for CO2, okay? I did the practice with hydrogen because I believe that most of you are more interested in hydrogen than CO2, but the steps are the same. You can follow the same step to get through this exercise, okay? I took the data from the Duan and Sun paper, the paper that I just mentioned, okay? I picked this temperature is 60 degrees C, okay? There is a broad range of pressure. The numbers, take a look, the number is much higher than for hydrogen. The salinity is the same, is one molality of 1, okay? The salinity is the same, the temperature is a little bit different, but the solubility are much greater than for CO2, for hydrogen. So the idea is the same. Go to improp, input the data, tune the solubility model. For CO2, you don't need to change much the range. I think you need to change a little bit the range of the boundary range of the parameters, and it should be much easier to get the match, okay, for CO2. So this is just my recommendation, my recommendation. And the general conclusions, we could use traditional equations such as Penke-Robson to predict density, JST to predict viscosity, and Li and Yu to predict solubility. Those are famous correlations and models traditionally used for hydrocarbon mixture, but we could use to represent mixtures that are typical in underground hydrogen storage. Okay, so we can bring a knowledge from classical petroleum applications and apply for underground hydrogen storage. For CCS, the same. Okay, the same thing. For CO2, we can use the same equation, the same models for computations. I think the point that you need to take care is the correction in the solubility for high salinity at high pressures. Okay. Yeah, I think the key message is this, and the traditional methods can be applied for storage project, even if you are working with CO2 or hydrogen. So, and those models are available in any commercial simulator. I use the WinProp here, but everything the same methodology can be done using PVT-Sim or PVT-P. Okay, it's the same thing. Thank you so much. I think this is my final slide.